3I Atlas is not behaving like any ordinary comet. First spotted racing into the solar system at impossible speed, it has since defied nearly every prediction. Its brightness is rising too quickly, its rotation is unnervingly steady, and its trajectory shows subtle deviations that strain standard models. The more data astronomers collect, the less it resembles anything they've ever seen before. Now comes the most unsettling clue of all: its estimated mass. Calculations suggest that 3I Atlas is far heavier than an icy body of its size should be. So massive, in fact, that if it continues to accumulate material at this rate, it could alter the delicate gravitational balance of the inner solar system. The key lies in what astronomers are not seeing. Comets that approach the Sun typically display non-gravitational accelerations, tiny but measurable pushes caused by jets of gas erupting from their surfaces. These deviations are so common that they are built into every orbital model. A1 for radial pushes, A2 for sideways drifts, A3 for out-of-plane kicks. These coefficients have been cataloged for decades, allowing scientists to refine predictions with remarkable accuracy. But 3I Atlas shows no such accelerations at all. Despite its visible activity, its orbit has remained purely gravitational, moving exactly as though no outgassing were occurring. For that to be true, its nucleus must be vastly more massive than expected. This is where the numbers become impossible to ignore. If an object a few kilometers across sheds material into space, yet its orbit does not change, then its core must be anchored by extraordinary weight. Current estimates place its minimum mass at more than 33 billion tons, far beyond the range of ordinary comets, which typically register orders of magnitude lighter. In practical terms, 3I Atlas may outweigh known comets by factors of 10, 50, even 100. Such a figure does not simply expand the margins of comet science, it breaks the framework entirely. Astronomers have long relied on the assumption that interstellar visitors would resemble the icy leftovers of our own Oort cloud, fragile, porous, and prone to disintegration. Oumuamua in 2017 challenged that view with its bizarre acceleration and elongated shape, but it still behaved like a small, lightweight body. Borisov in 2019 reassured many by acting like a textbook comet, albeit with exotic chemistry. But 3I Atlas changes the game entirely. Instead of being fragile, it appears durable. Instead of light, it appears dense. Instead of being a fleeting wisp of interstellar rubble, it looms as an interstellar heavyweight. And that raises an extraordinary set of questions. How does such a massive body form between the stars? Was it born in the violent birth of another planetary system, hurled into interstellar space by the gravitational chaos of giant planets? Could it be a fragment of a failed planet, a shard of primordial rock and ice that survived for billions of years on its journey here? Or is something stranger at work? An object not just surviving, but perhaps growing, feeding off its environment in ways we do not yet understand. The brightness curve fuels these speculations. 3I Atlas is growing brighter at a rate inconsistent with ordinary sublimation. A comet sheds surface ice as it nears the Sun, producing jets that cause both brightening and orbital deviations. But here, the glow is rising without the corresponding drift. One interpretation is that its surface area is increasing, either because it is shedding fragments or because it is expanding in ways not yet understood. Another, more daring interpretation is that the object is accumulating dust and gas rather than losing it, sweeping up material as it travels, increasing its effective cross-section. If true, then the mass of 3I Atlas could be actively rising, not just anomalously large at the start. The consequences of such growth would be profound. Even a modest increase in its effective size could amplify its gravitational influence, tugging subtly on nearby bodies as it swings through the solar system. The asteroid belt, with its delicate orbital resonances, could feel the nudge. Mars, on its near path to the object, might experience minute shifts in its orbital timing, imperceptible in the short term, but cumulative over centuries. Earth itself, though farther away, is not immune to such perturbations. The solar system is a web of balances, and a massive interstellar visitor could pluck at those threads in ways we are only beginning to imagine. This is not idle speculation. The history of astronomy is filled with examples of how small gravitational perturbations can have outsized consequences.
Neptune itself was discovered because of tiny deviations in Uranus's orbit. The stability of the asteroid belt depends on subtle resonances with Jupiter, repeated over millions of years. A single interstellar body of sufficient mass passing through the system has the potential to inject new chaos into this carefully tuned architecture. That is why the suggestion of a 33 billion-ton visitor has stirred such unease.
What makes the case more unsettling is that the usual escape routes for interpretation are closed. Outgassing cannot explain it. The lack of non-gravitational acceleration rules that out. Measurement error seems unlikely given that independent observatories across continents, from Hawaii to Chile to Europe, have confirmed the same readings. Instrument artifacts are always a possibility, but the consistency across telescopes and analyses pipelines suggests otherwise. What remains is the simple, unnerving conclusion: 3I Atlas is massive, far more so than it has any right to be. Speculation naturally fills the void left by data. Some theorists point to exotic chemistry. The object is dominated by carbon dioxide, with water ice playing a surprisingly minor role. Such composition could produce strange thermal properties, perhaps accounting for its stability and brightness. Others propose crystalline ices layered in complex structures, able to store and release energy in cycles that mimic regularity. But none of these explanations account for mass on this scale. Chemistry can explain color, activity, and volatility, but not sheer weight. This is where the vessel hypothesis reemerges, not as wild fantasy, but as one of several possible scenarios. If an object has the density and mass to resist outgassing effects entirely, then one possibility is that it contains large amounts of metals or other dense materials. A natural explanation might be a fragment of a planetary core, torn from a world in some distant system. But another possibility is artificiality, a structure built to endure, perhaps even to travel. If so, then the absence of orbital deviations is not a mystery at all. It would be the expected outcome of a craft designed to maintain course, immune to the trivial forces that buffet fragile comets. Astronomers tread carefully here. The weight of scientific history presses against extraordinary claims. For every anomaly, the instinct is to seek the most mundane explanation. Yet history also reminds us that anomalies are the engines of discovery. Oumuamua taught us that interstellar visitors need not fit familiar molds. Borisov showed that chemistry beyond the solar system can be stranger than anticipated. Now, 3I Atlas challenges us to reckon with mass itself, with the possibility that some interstellar travelers are not wisps of dust and ice, but giants, capable of reshaping planetary systems in their wake. The implications for planetary defense are immediate. Current models of impact risk assume comets are fragile, likely to fragment under stress, dissipating their energy across multiple pieces. Deflection strategies are designed accordingly: kinetic impactors, gravity tractors, or in extreme scenarios, nuclear devices. But how does one deflect an object whose mass dwarfs anything in the known catalog? How do you prepare for a body that does not shatter easily, but endures? These are not abstract questions. If 3I Atlas were on a collision course with Earth, the usual playbook might be useless. Even without a direct collision, its gravitational influence alone could pose new challenges for space navigation, orbital stability, and the safety of satellites. Mars, however, remains the most immediate concern. Orbital projections suggest 3I Atlas will pass within a few million kilometers of the red planet, a close shave in cosmic terms. If it continues to brighten and expand, if it sheds or accretes material in unpredictable ways, the encounter could be transformative. Debris could rain onto the Martian surface, atmospheric shock waves could alter weather patterns, rovers and orbiters could be exposed to dust storms of interstellar origin, and beyond the science, the symbolism looms large. Humanity's long-planned outpost in the solar system may find itself sharing its skies with a visitor from beyond the stars.
Earth is farther away, but not beyond risk. The solar wind is not empty space. It is a constant stream of charged particles flowing outward from the Sun at hundreds of kilometers per second. It acts like a vast conveyor belt, carrying disturbances across the solar system. If 3I Atlas were to release massive amounts of dust, ionized gas, or plasma, those materials would not simply disperse harmlessly. They could ride this current directly into the heliospheric highway, spreading outward until they intersect with planetary magnetic fields. For Earth, that would mean a sudden influx of high-energy particles slamming into our magnetosphere, compressing it, warping it, and unleashing chaos within our upper atmosphere. The result would not come in the form of a blazing fireball or a cratered surface. It would arrive invisibly, silently, in the form of electromagnetic disruption. Satellites could be disabled, their circuitry fried by charged particle bombardment. GPS networks, already vulnerable to solar storms, could fail entirely. Communication systems could collapse, navigation signals could vanish, and aviation routes could be thrown into disarray. Power grids, the fragile skeleton of modern civilization, could buckle under the pressure of geomagnetically induced currents. Transformers could burn out, leaving cities in darkness not for hours, but potentially for weeks or months. The Carrington event of 1859 remains the starkest reminder of what such storms can do. That single solar flare caused telegraph systems across Europe and North America to spark, overheat, and fail. Operators reported electric shocks, and in some places, telegraph machines continued to send messages even after being disconnected from their power supplies. If such a storm struck today, with our dependence on digital infrastructure, the damage would be measured not in sparks and broken wires, but in trillions of dollars and cascading failures across global economies. And while the Sun has always been the culprit in these events, the prospect of an interstellar body triggering a similar or even larger surge is something unprecedented and unpredictable. This looming possibility is why astronomers are treating 3I Atlas as more than just a curiosity. It has become the subject of an urgent worldwide campaign of observation. Hubble continues to monitor its brightness variations, searching for patterns that might reveal whether its glow comes from outgassing or something more exotic. The James Webb Space Telescope has been retasked to study its chemistry, probing the infrared spectrum for fingerprints of unusual compounds that could hint at its true composition. Ground-based observatories, from Chile's deserts to Hawaii's volcanic peaks, are feeding a steady stream of astrometric data into global tracking networks, refining orbital models with every passing night. Every telescope that can be spared is pointed at this visitor. Each image, each spectrum, each line of data is another piece in a puzzle that seems to grow stranger with every attempt to solve it. But for all this effort, certainty remains elusive. The closer 3I Atlas comes, the more anomalies it reveals, and the more the models begin to fracture. Instead of narrowing toward a clear explanation, the possibilities only widen: natural, exotic, engineered, catastrophic. The object defies easy categorization, and in doing so, it forces humanity to confront not only scientific puzzles, but existential ones. And so the debate continues. Is it an oversized natural fragment? A shard of some lost world? Is it a collector of material, growing as it sweeps through the solar system? Is it an engineered structure built to endure the void? Or is it something entirely outside the categories we know? Each possibility carries its own implications, and none are reassuring. What is clear is that we are witnessing something unprecedented, a visitor whose mass is so extraordinary that it cannot be ignored. The story of 3I Atlas is still unfolding. In the coming weeks and months, new observations will refine our understanding, perhaps ruling out the most extreme interpretations, or perhaps reinforcing them. But whatever the final answer, one fact is already certain. With its sheer weight, with its unyielding trajectory, with its refusal to fit the mold of any comet ever seen, 3I Atlas has forced humanity to look at the cosmos differently. It is not just a curiosity passing through, it is a challenge. A reminder that the universe is not obligated to match our expectations, and that sometimes what arrives from the stars can upend not only our theories, but the balance of the solar system itself. For now, the object races onward, silent but impossibly heavy, a dark mass cutting across the heavens. Its future path is known, but its true nature is not. Comet, fragment, vessel, or something we have no words for yet. 3i Atlas carries with it a question whose answer may reshape the story of humanity's place among the stars.